This is HRW913P021. We've got a certain neutron stars are believed to be rotating about 50 revolutions per second. If such a star has a radius of 5 kilometers, what must be its minimum mass so that material on its surface remains in place during the rapid rotation? Okay, so I went ahead and wrote down the numbers they give us. So angular velocity 50 revolutions per second, radius of 5 kilometers. Okay, go full screen now. Oh, I put it on the wrong side. Oh well. Okay, so what I've really got going on here is I have, if this is the star, I'm going to show how it's shown from above. So here's the axis, and this thing is rotating. Okay, it's rotating with some radius, and it's got some radius r. Let's say we have some mass on the surface of mass small m. I want to find the mass of the star big M. What I basically have here is I've got a mass traveling in a circle of radius r. So it needs a centripetal force. It needs a centripetal force that's enough to keep it moving in this circle. That centripetal force needs to be provided by some other force, in this case, the gravity of the neutron star. So basically, the gravity could be more, but it needs to be at least the same as the centripetal force. So what I really have going on is the force of gravity needs to be at least as big as the centripetal force, like that. Well, the force of gravity, it's G, big G, times the two masses divided by the distance between their centers. So the little mass is here, the distance to the center of big mass is r. So that needs to be more than or equal to the centripetal force. Centripetal force for something moving in a circle at an angular speed of omega is mass. Oops. Oh, that was weird. It just collapsed. Did you see that? Weird. Okay, anyway, omega squared times the radius of the circle it's traveling, which just so happens to be the same r as in the gravitational equation. Okay, so first off, while I got mass on both sides, I can get rid of it. Alrighty. Now I need to solve for m, get m alone, since that's what I'm looking for. Oh, I forgot to write that. M is what I'm looking for, big M. Alrighty, so let's see, multiply both sides by r squared and divide by g. So, oops, that is the wrong color. Must stay color coded. Okay, so the mass of the star is going to be greater than or equal to, let's see, multiply by r squared, divide by g. I end up with omega squared r cubed over gravitational constant. Alright, all I have to do is put numbers in. I do have a little bit of a problem though. My numbers are not in standard units. I need them to be in standard units. So, okay, omega, well, it's in revolutions per second. I need it to be in radians per second. So I'm going to use that 50 revolutions per second, but I'm going to multiply by how many radians are in a revolution. One revolution is all the way around a circle, so that is 2 pi radians. Revolutions go away, and I end up with that omega is really 100 pi radians per second. Okay, so over here I've got 100 pi radians per second. Come on, that's squared. Don't forget the square. R also not proper. R needs to be in meters, not kilometers. Well, that's easy enough. I just multiply by 1,000, so I'm not going to do anything fancy. It just becomes 5,000 meters. So when I plug that in, sorry, my cat is being adorable because they're out of food, but they don't get fed for another, what is it, 6 a.m.? A long time. 6 a.m. they get fed at 1500, so like 9 hours. And I already cheated. I already gave them extra food. They are on a diet. Okay, anyways, it's 6 a.m. Why am I doing this at 6 a.m.? I don't know. 5,000 meters cubit, and g is 6.67 times 10 to the negative 11. No, Charlie. I'm sorry, Charlie. No. Okay. That I put that in, and I get the mass of the star is greater than or equal to. Let's see. It comes out as 1.85 times 10 to the 26th. And since all of our stuff was in standard units, my answer should be in standard units, which is kilograms. So that should be the answer. Let's check it. Yep, that's the answer. So, we're done. Go. Huh? Yes, Charlie, I'm coming over there.